Hello, everybody, and welcome back to PreCalculus with Mr. Beck. I am Mr. Beck, and I've got your back, and you've got your back. So what I'm planning to do today we're going to be looking at a little bit about Chapter 8. Today's a kind of review day. We're going to look at different story problems that we've experienced throughout the entire chapter, all thrown together. Who knows what we're going to do with all these problems. First one we're going to take a look at is a hot air balloon. It's rising vertically from a point 250 feet from the ground where the balloon took off. As with any story problem, I'm just going to stop right there and say, okay, let's draw a picture. So I have a balloon that is taking off right here, and that is 250 feet away. And now from that point, the angle of elevation to the balloon is 18.4 degrees. So if I draw 18.4 degrees, I have something that looks about like that. And then after the hot air balloon rises for 1 minute, 1 minute, let's take off the S off of that. So after it rises for 1 minute, the angle of elevation changes to 46.8 degrees. So I have a second situation where I'm still 250 feet away, but now the balloon's risen a lot higher, and we have 46.8 degrees to that angle of elevation. So this is a little bit of a review of what angle of elevation is. So my question is, how far to the nearest thousandth of a foot does a balloon rise during this period? So my question is, if I start off at that height and I end up at this height, how far did it rise? And my big idea here is we're going to take y minus x. How are we going to do this? Well, what relationship do I know between all three pieces of this triangle? I have that angle, I have the opposite side and the adjacent side. That shouts out to me, we're talking tangent. So the tangent of 18.4 degrees will equal x over 250. And if I solve for x will equal 250 times the tangent of 18.4 degrees. I have my calculator up and ready. So I take 250 times the tangent of 18.4. Let's actually type that in now. 250 tangent of 18.4. It looks like I get a height of about 83.164 feet. So I will be subtracting out the 83.164 feet. Similarly, if I take a look at the second triangle, I could take the tangent of 46.8 degrees equals y over 250, or just write out y equals 250 tangent of 46.8 degrees. So 250 tangent of 46.8. And I forgot my parentheses. That looks better. And I get 266.223. So 266.223. If I take that and subtract, so take that and subtract the 83.1639, I get that the balloon traveled 183.059 feet. All right, question number one answered. Question number two, what is the average speed of the balloon both in feet per second and miles per hour? Average speed. So I need to take a look and remember what is average speed. Average speed is going to be the total distance divided by the total time. And the total distance is that 183.059 feet. And my total time, it was 1 minute. 1 minute, but I want feet per second. So that would be 60 seconds. So I will take my answer there and divide it by 60. And I get 3.051. So 3.051 feet per second. So that is question number one answered on that part. And then I also wanted in miles per hour. Miles per hour, I need to work with some dimensional analysis. So I need to know relationships between feet per second and miles per hour. So I do know that there are, let's see, if I want to go from seconds to hours, there are 3,600 seconds per hour. So now if I do my dimensional analysis, I'm left with feet per hour, but I really want miles per hour. So I need to say there is 1 mile in 5,280 feet. So again, my dimensional analysis, I'm left with my units of miles per hour. And I will start off with that answer that I had before. And I will multiply by 3,600 and divide by 5,280. And I get 2.080. So 2.080 miles per hour. So very slow moving balloon. Kind of makes sense to me. So that was a little bit of review of 8.1 and then just throwing some extra stuff with it. And one of the things I like about throwing these extra kind of problems is this kind of stuff comes up in calculus quite a bit. We're talking about average rate of change and then instantaneous rate of change. This is just kind of like a preview and application, which is what PreCalculus is about. Question number 2, I have 2 ships leaving harbor at the same time, traveling for 4 hours. What I wanted to do with this problem was bring back into mind some kind of bearing, because we didn't get to do a lot of homework practice with the bearing, so more and more practice that we have here is going to be better for all of us. So I have these 2 ships leaving harbor at the same time. One is going 18 degrees west of south, and the other one is going 39 degrees east of south. So, as always, let's draw a picture. And I'm going to say the harbor is right there. Ship A traveled 18 degrees west of south and is going in this direction. So 18 degrees looks about like that. So let's make that 18. And how far did this ship travel? As I take a look, I know it's going 4 hours at 20 miles per hour. So 4 times 20, A is going 4 times 20, which is 80. So that distance right there is 80. Ship B is 39 degrees east of south. So 39 degrees is roughly, let's say that angle, 39 degrees. And how far does this ship travel? 4 hours times 18 miles per hour. 4 times 18, just as a quick in my calculator, I should know this, 72. Doesn't hurt to write that down, 72. So ship A is right here, and ship B is right here. And now our situation, ship A hits a sandbar and is shipwrecked. How far does ship B have to sail in order to save the crew of ship A? So what's going to happen is my crew in B have to travel all the way to A. So they're going over there, and I want to know how far they have to travel. So this is a review of a side angle side triangle. And if we have a side angle side triangle, that means we're going to be using our law of cosines. All right, law of cosines, if I remember, I'm going to call this side H, which is opposite of my harbor. If I want to find my H squared, I'm going to take my other 2 sides squared, so 80 squared plus 72 squared, minus twice the product of those 2 sides times the cosine of that angle. Now, quick question, was that angle? That angle is 18 plus 39, which gives me 57. And so I'm left to, let's type it in the calculator. So I will have 80 squared, so 80 squared plus 72 squared. 82 squared plus 72 squared. And then it'll be minus 2 times 80 times 72. And that would be times the cosine of the angle in between, which is 57. And I need to make sure I put a decimal point in here. And I get that number. But I don't want that number because that seems too large. I need the square root of that number. 72 miles seems to make a lot of sense. So 72.868. Right, so really, that side should be pretty close to what should be traveled. So I'm probably going to be thinking these angles are the same, just kind of like as what I'm looking at. Part B, what bearing? So let me actually write this out. So H, or the distance between these two ships, is 72.868, and that would be miles. All right, question B, what bearing must ship B head to for the rescue of the ship A crew? So now I get my bearing problem again. And what I'm going to do is I'm going to recreate this drawing where I have ship A here, I have ship B here. Now, the moment I have bearing, I'm going to need to make sure I draw a new north-south axis. And the harbor was up here and came down at that angle. Now, what I'm looking at, the harbor was up here, and this was a 39-degree angle that was part of the bearing of ship B originally. Now, the reason why I want to draw my north and south axis every single time is because this north-south axis creates, if you remember from geometry, two parallel lines. Two parallel lines are going to be cut by a transversal, meaning this path that should be traveled is the transversal. So what I'm left with, I know that this is a 39-degree angle right here as well because of alternate interior angles. Now, my goal is to find the bearing of ship B to ship A, which is this. And the reason why I need to know that 39-degree angle is because once I solve my triangle for angle B, I'm going to work with that 180 degrees in that full line to figure out what my unknown bearing is going to be. So let's go ahead and solve for angle B in the triangle. To solve for angle B in the triangle, I'm going to be using my law of sines. So I'm recreating this triangle one more time, but do this kind of quickly. I have something that looks like this. I know this is 80, I know this is 72, and this is 72.868. And I know that this is a 57-degree angle. Now, if I'm going to be using the law of sines, which is our 8.2 review, our law of sines, we have to work with, and this is where a lot of people don't remember this right away, is I want to make sure I use my law of sines to solve that side. And the reason is because I know that this angle has to be acute if it's opposite the smallest side. So when I use my law of sines, I will say the sine of that angle, which that is angle A. So the sine of angle A over the 72 will equal the sine of 57 degrees over the 72.868, which gives us A is 72 sine of 57 over 72.868. And that would be the sine of A. I actually want the inverse sine of that whole expression. So let me just rewrite inverse sine of that entire expression. And let's throw this into the calculator. I want the inverse sine of 72 times the sine of 57 degrees and divide that by 72.868. And it just occurred to me I'd rather keep the exact value. So angle A is 55.9633. And now to find angle B, I will take 180 minus the 57 minus that 55.9633. Let me type that out. 180 minus 57 minus 55.96. Once again, just go ahead, scroll up. And I get angle B is 67.0367 degrees. Now, what that means is I was probably a little too cautious. So my goal is to find angle B. I was too cautious that I probably could use the law of sines at angle B and would have been okay because angle B is an acute angle also. But the big question, because this is the ambiguity, what I was working with was I had or if I were to find angle B, I would be working with, let's see, I know this piece, I know, see, I know this piece and I know this piece. Were those the three? Nope, it was these. So that was working with the side-side angle, which is where ambiguity comes into play. Again, I was being overly cautious with that, but at the same time, I strongly encourage that kind of caution. That way we know that we're guaranteed to have the correct triangle that we're working with. So anyway, angle B was 67.0367 degrees. That would be right here, 67.0367. Now, what was the overall goal of what I was trying to find? I got so lost in solving this triangle just because I have so much fun solving these triangles. My goal was to find the bearing, which once again is this piece right here. So to find that, I will take 180 minus that angle that I just found, and then minus 39 degrees that I originally had. And that bearing should now be, so this is 180 minus the 67.0367 minus the 39. So that is a 73.963 degree angle. So my bearing is south, 73.963 degrees to the west. A lot of work just to find that one problem, but kind of important thing to know. Because a lot of times when you have two ships, or really when you have two pieces of information all looking at the common goal, or the common in this case was a harbor, we want to know all those distances. We're going to have to use bearings to figure out how to get from one place to another. One last problem I have for you. Today's notes are a little bit shorter. One last problem that I have for you involves one of my favorite pastimes over the summer is I do like to take my kids camping at different state parks. And one of the things I've seen in a variety of the state parks that I've been in are these Indiana fire towers. Indiana first began to build these in 1930 to detect forest fires, and they'd send these resources, meaning the planes, basically to put these fires out. They made a total of 33 fire towers, but there are only 13 left standing, and I've climbed 3 of them, I believe. I've seen 3 other ones, mainly in southern Indiana, which is where we like to camp over the summer. So this problem I have here is a real life problem of solving triangles that Indiana actually had. So I'd like to conclude chapter 8 with a real life problem. So what I've done is I've focused on the small portion of southern Indiana. Small portion of southern Indiana is going to be down in this area. Actually, I think that was a little too wide of an area, so that's okay. So it's going to be overall in that area. Anyway, a fire breaks out in the Hoosier Forest. So let me change color really quickly. So I can say I have my Hoosier National Forest, which is right here, and the fire breaks out. So I'm going to do this in orange. The fire breaks out right here. Let's call that F for fire. And then I probably should not call that F for fire, but too late. The Ferdinand Tower and the O'Bannon Woods Tower, and those 2 towers, let's kind of call attention to where those 2 towers are. First of all, if you see in blue right here, that's Ferdinand. So this is where I was like, fire maybe should have been called F. Let's call that P for the Ferdinand Tower. And then we have the O'Bannon Woods Tower. The O'Bannon Woods Tower is near Corydon. And just some Indiana history for you, that used to be the capital of Indiana. Let's call that O for the O'Bannon Woods Tower. Those 2 towers respond to the fire. Now, the bearing from the Ferdinand Tower to the O'Bannon Woods Tower is 80 degrees east of south. So what I'm looking at is this, and this is 80 degrees right here. And they are about 30 miles, that's supposed to be they are about 30 miles apart. Let's quickly correct some grammar there. They're about 30 miles apart. So that is 30 right here. The bearing from Ferdinand Tower to the fire is 65 degrees east of north. So this right here should be 65 degrees. And then the bearing from the O'Bannon Woods Tower to the fire is 50 degrees west of north. So that would be 50 right there. Our goal, find the distance from each tower to the fire. So in order for me to do this, what I would like to do is I'd like to recreate this triangle a little bit, just because that's too dark for me to effectively work with. So if I'm going to recreate the triangle, that looks about right. And if I'm not 100% accurate, it's not the end of the world. There we go. And this is what I call T. I'll call that for the Ferdinand Tower. This is the O'Bannon Woods Tower. And then this is my fire. I know this is 30. Now, again, the reason why I wanted to redraw this is just so that I could redraw my north and south, or my north, south, east, west axis for each one of these. I want to draw this so that I have room to write. I could not do that in the picture that I had up there. All right, so now that I have my north-south axis for each one, let's fill in what I know. I know that this was a 65-degree angle. And again, the reason why I need these north-south is so that I have my parallel lines, which creates the alternate interior angle of 65 right here. I also know that this is 80 degrees right here, which leaves us a 10-degree angle right there. Now that 10-degree angle also will lead us yield a 10-degree angle right here. Again, alternate interior angles. I do know that one more thing, this is 50 degrees right here, which gives me an alternate interior angle of 50 degrees right here. And so now I believe that's all the pieces that I know, and our goal is to find the distances from each tower to the fire. So our two distances that I want to know, I'm going to call this one T. That T represents the distance to the Ferdinand Tower. And then I'm going to call this side little o, because that's from the O'Bannon Woods Tower to that fire, or to the fire. So with this overall situation, how do I approach it? Let's take a look and say, I know this combined angle right here, and I know its opposite side. And which tower do I want to find first? Let's find the Ferdinand Tower, which is opposite this angle. So I have to find what that angle is. If I know that this is 50 degrees right here, and this is 10 degrees right here, 50 plus 10 is 60. So this is giving me a 30-degree angle right here. Let me actually do that in a different color so you know what else I found. So that's a 30-degree angle. So I will take the sine of 30 over that Ferdinand Tower distance equals the sine of, quick, what is 65 plus 50? That would be 115 over 30. Was that distance 30? So they're about 30 miles apart, yep. So quick flip, if you remember, t over the sine of 30 will equal 30 over the sine of 115. So t is going to equal 30 sine of 30 over the sine of 115. Let's throw that in the calculator. So 30 sine of 30. That's a little confusing, but that's okay. We know that that first 30 is a distance, that second 30 is an angle, over the sine of 115. And once again, I need to make sure I put a decimal. And I get that that Ferdinand Tower is about 16.551 miles. So 16.551 miles. And with the O'Bannon Woods Tower, I'm going to do something similar. I'm just going to start from here and say O over the sine of, I don't know that angle yet. So if this is 65 degrees here, 65 plus 25 gives me the 90-degree angle. So this overall angle is 35 degrees, 35. So O over the sine of 35 will equal 30 over the sine of 115. So O is, and that was 35, I wrote 33. O is 30 sine of 35 divided by sine of 115. Throw that in the calculator. So 30 sine of 35 divided by 115. We get O is about 18.9861 miles. So the distance to the Ferdinand Tower is about 16.5 miles. The distance to the O'Bannon Woods Tower is about almost 19 miles. Now, I hope this gave you insight into a little bit of Indiana history, which is always a fun thing to have. Some nice pictures of some of the different towers. They really are beautiful. Southern Indiana is a beautiful place. You see a lot of those towers really are in Southern Indiana. But I hope you enjoyed these notes. Remember, pre-calc with Mr. Beck, and I've got your back, and you've got your back. Have a good day.